the discussion will be, what can we say about the properties of a magnetic Vison as a quantum particle? And the work which I present today has been all done here by my student, Achim Rosch, so all credit goes to him. Let me start with a kind of general introduction, and I want to ask the question, when we look at the laws of physics, and they are largely gauge theories, and an obvious question is, oh, there's a problem. So we want to ask, where are gauge theories coming from? And there's a traditional answer to this question from high energy physics, which says, well, gauge theories are coming from gauge theories. So, no, this is not working anymore. Not good. Aha. So gauge theory is coming from gauge theories. So U1 gauge theory comes from a U1 cross SU2 gauge theories. All the stuff, or the standard model may come from some grand unified theory or theory of everything. So that's the possible answer, that gauge theories come from gauge theories. But in recent, let's say 20 years, we have found out that there's another option to answer this question. Namely, there's something called emergent gauge theory. So how do we get now emergent gauge theories, which are also in theory everywhere? What you do is you start from some non-gauge theory, let's say a model of interacting electrons or spins, and then you continue by introducing some unphysical redundant degree of freedom. Yeah, you introduce Majorana fermions, slave particles, whatever. And then when you write this looks like a gauge theory automatically. But now you're not yet done. Namely, the real question is not whether you can rewrite a theory as a gauge theory, but whether the effective low energy degrees of freedom really carry the right gauge charges, and whether the gauge field is really a physical object. And so we have to ask the question, can we have a really deconfined emergent gauge theory where this gauge degree of freedoms become physical? Now, do we have such examples of such theories in solid state physics? And we all know the answer is yes, and we've seen several examples today. So actually there are, I don't know how many examples we have by now, maybe hundreds of examples of varying rigor. So in some cases we know it for sure. In some cases, there's some numerical evidence. In some cases, it's just wishful thinking. But we have plenty of well-established examples of emergent gauge theories. Unfortunately, on the experimental side, the situation is not so nice, I would say, and maybe some in the audience will disagree. But my impression is that we have, we have lots of candidate systems. All are, at the end of the day, controversial for one reason or the other. And I think one of the holy grails of condensed matter physics is find one system where we really have clear experimental evidence for emergent dynamical gauge fields. So this is for me what, if you want to have a top list of most important goals in modern condensed matter physics, that would be my prime wish for the experimental physicists. Good, let's take a look at one of the models which now theorists like most, and we have seen this today, so I can be brief. This is famous Kitaev model, and you all know by now how this looks like. So we have spins on a honeycomb lattice, and they have this very specific bond-dependent interaction, and it's wonderful because we can solve exactly and find out everything what we want to know about this idealized model. Good, and let me just still, I know you know that, but let me still remind you how this goes. So what you do is you write the spin in terms of 4 Majorana fermions. Thereby, you have actually doubled the Hilbert space, introduced redundant degrees of freedom. And then you realize that you can interpret the resulting system as a gauge theory. Yeah? So there's one set of Majoranas and a gauge connection, and this has a gauge symmetry, C2 gauge theory. So you can multiply this by ±1, which defines this model. And now comes an important step, maybe which you haven't, which is often not so discussed, but I think is very an important step in solving of this gauge theory. What you then do is that you say, oh, because all gauge configurations are identical, I do not have to do what's written above here, namely I do not have implement the constraint, which would be equivalent to sum over all gauge sectors. But instead, I can fix the gauge and then look for propagating Majoranas, for example, in a fixed gauge sector. That's how the solution goes. And yeah, and then it becomes very easy because the Majorana Hamiltonian is just quadratic. Yeah, and here's how the low energy degrees of freedom look like. So the Majorana fermions, they form a Dirac dispersion, and on each plaquette, you have now this extra gauge degree of freedom, which is the flux, which you can either write in terms of these physical observables or in terms of this gauge degrees of freedom. And we have now two options for each plaquette. We either have a flux or we don't have a flux. Good. And this is now, this talk is about this flux. It's got a name, it's called Vison. And with Vison, we mean now not this flux, but it's really this flux stressed by its environment. So it's a kind of Cologne style state. This flux stressed by these scattering Majoranas. Good. Now, a very important point is this Kitaev model has an artifact, namely that this flux is a conserved quantity. So this beast is not moving, it stays always at the same point, and obviously we want to work on that in this talk. Good. So what about a short experimental motivation, remarks on that? And we heard some of that from Natalia already this morning, but I want to give a different, I want to show you a different system, which is my personal favorite in the context. And there's this ruthenium trichloride, and there have been reports that when you apply a magnetic field, then there is a phase developing with a half-integer thermal quantum Hall effect. So yeah, so here's such a measurement. So this is a measurement of the thermal transverse transport as function of magnetic field. And you see in these experiments, there's a regime where you get this plateau like value in a very limited field and temperature range. And when you look what this number is here, this plateau number, then you realize it corresponds to 1/2 of a thermal conductance quantum per layer in this system. And yeah, now I have to say this is a very controversial. So I say all experiments are controversial, and this is also one of these controversial experiments. So there have been now many different papers reporting either quantization or non-quantization. So there's a series of works which reported some version of quantization, and there's another series of work which find other results. And it's not today's topic. There's some, let me say, from point of theory, it is actually expected that you see this thermal Hall effect only when there's precisely the right level of disorder, not too strong and not too weak. So it may be not too surprising that different groups get different results, but at the moment, this is still an open question. But you want to take the kind of positive view and say, oh, we have an obvious theory for this type of system. Namely, if you take a good old Kitaev model and put it in a magnetic field, then you find out immediately that these Majoranas are gapped out, and you naturally get a half-integer thermal Hall effect, because on the edge of a gap bulk, you find a Majorana mode which encircles the system, and that precisely gives you a half-integer quantum Hall effect. Good. So I said the obvious theory is a Kitaev model in a magnetic field, but this is not really true. And that's the point of this talk. Namely, what you should think of is not about the Kitaev model in a magnetic field, but you should think about the Kitaev liquid in a magnetic field. What do I mean by that? This Kitaev model is full of artifacts, and what we can ask is the following question. Let's start from the Kitaev model and add all types of symmetry allowed perturbations, and then ask what type of interacting many-body systems do we get out of that? And this is what we want to know, and we want to understand its properties. So let me do a comparison of Kitaev model and Kitaev liquid as just defined. So we started from the fact Kitaev model is exactly solvable, and Kitaev liquid, we said, let's add these perturbations. For example, first thing you may want to look at is at the Majorana fermions, and they are non-interacting in the Kitaev model. Now, in the generic spin liquid, obviously they get some interactions, but it turns out these interactions are irrelevant in the renormalization group sense, which means perturbation theory works and they don't change so much of the physics. A more dramatic difference is when you look at the spin gap in the system. It turns out when you start to flip a spin, then you create one of these massive excitations, the Vison. So you create a pair of flux which costs a finite amount of energy. While when you look what happens in the generic spin liquid, then this is not true, as pointed out in this paper. Namely, you can actually, when you flip a spin, you don't have to create any Visons. You can also just create a pair of Majoranas. A very dramatic difference. The real thing doesn't have a spin gap, while the Kitaev model does have a spin gap. And a very similar story is when you apply magnetic fields, then in the pure Kitaev model, the gap opens to third power in the magnetic field, while in the generic Kitaev model, this gap opens linear in the magnetic field for more or less the same reason. And the point which we want to focus on is that in the Kitaev model, the gauge field is completely static. But obviously, it gets dynamical in the generic Kitaev liquid. And the question, and what I wanted to do is, today I want to resolve this question mark here. Namely, here we said the Vison is just a gapped localized excitations, and now we want to show what we get instead. So we want to know question, is this Vison a well-defined quasi-particle? Does it have band structure? Does it have interactions? What are its mobilities? And ultimately, what are experimental signatures? So that's a program for today. And so there's very clear what one should do. Namely, we start from the Kitaev model and we add small perturbations. Yeah? And small perturbations are typically a gamma term, a symmetric gamma term, Heisenberg interactions, or magnetic fields. Yeah? And then we want to see what happens. And we start with the most obvious thing, which is linear order perturbation theory. Yeah? So let's say we have the Vison here being localized at one position, and now we want to see whether we can hop it via the perturbation to a different position. And these wave functions now to the left and the right, they are these many-body ground states of the Kitaev models, which is the Majorana fermion scattering from a flux, from a static flux. Let me just briefly mention that this calculation of this this overlap actually turns to be out more subtle than I thought. So you have actually to work a little bit to do that. So you start from this Majorana state, which is a wave function describing the scattering of the Visons, of the Majoranas from the Vison. And then you have to think about what the gauge sector is. You have to introduce projection operators to the physical state. But when everything is said and done, you can set up a merx, let's say on some few thousand sites. It's non-interacting model, so it's very easy. And you can express these matrix elements in terms of some Pfaffian, which you calculate from your scattering problem. Good. So let's look at one of these terms. So let's say we have a Vison, a flux localized here, and we want to move it here. And we take this gamma perturbation, which is defined on this link. And there are two terms actually which move the Vison from here to here. Now, when you have two terms, which are symmetry, by symmetry have the equal amplitude, there are two options. You can have either constructive interference or destructive interference. It's a double slit experiment. So question is, what happens here? And answer is, that depends on whether you have the ferromagnetic or the antiferromagnetic Kitaev model. In the ferromagnetic Kitaev model, these two processes add up and get an efficient hopping mechanism. While in the antiferromagnetic Kitaev model, there's a destructive interference of the two parts, and therefore there is no coherent hopping to linear order. Yeah, and that immediately, without further calculations, that already explains one of the basic observations which has been seen in many numeric studies. Namely, the ferromagnetic Kitaev model is much less stable to perturbations compared to the antiferromagnetic one. That's because the Vison gains kinetic energy, reduces its gap closes much easier. because while this physics is absent in the other model because of this interference effect. Yeah, so it's a very qualitative, simple effect, but with important consequence, and will show up also later in the talk. Yes. Yes. No, I said okay, so. So now you're confusing me, but I'm sure that we looked this up 2 or 3 times. So I'm now confused also, but we have to look it up, yeah. But it comes out as it should come out. Good. So here's the so now you can calculate the spring rate, and well, you see here it has almost to calculate this for finite size. This thing has really no finite size effects whatsoever. And I'm emphasizing this because we'll later have another case. And so you precisely know what the hopping rate is now for the ferromagnetic model, and then you can easily calculate the band structure, and yeah, which is not very spectacular. You have some band structure with some minima, and that's it. Good. This was perturbation by the gamma term. Short comment when you do the same thing for the Heisenberg term. There turns out that again, due to some interference effects, all terms linear, quadratic, cubic order vanish, and you only get hopping to 4th order. So if you do only if you're interested in single Vison dynamics, you can just forget the J term and concentrate on the gamma term, and you're good if you have a weakly perturbed Kitaev model. Good. So now we said, oh, we have a finite hopping of this Vison, but we are not yet done, because this Vison will scatter strongly from the Majorana fermions, yeah, in a very singular way. And the question is it nevertheless a well-defined quasi-particle or not? That's not obvious, and that's because scattering from a flux is something very singular in general. So let's try to calculate that, and the quantity we want to consider is mobility of the Vison, or equivalently the diffusion constant of the Vison at finite temperature. Yeah? So that's the quantity we are interested in. Good. So it turns out that this problem can be solved exactly in quotation marks, so isotropically exact. And this is with a combination of bit of luck and some known results. So for example, Aronov-Boben worked out for us the cross-section of particles scattering from a flux. And this cross-section is very singular. It has this 1/k divergence and has also a strong divergence at small angles. But what helps you to solve the problem is that the transferred momentum in such a scattering process is always at low temperatures much smaller than the typical momentum of a Vison. Yeah, that helps you, and also that these Visons are obviously much slower than the Majorana fermions. And then the last thing which helps is that the Majorana density becomes low at low temperature. Yeah, so, and all these things conspire so that at the end of the day, you can describe the singular scattering of the Vison from the Majoranas by a Boltzmann equation here for the Vison or cohesion number, but the right-hand side, so the scattering kernel on the right-hand side looks a little bit different from what you're used to. It's kind of a diffusion in momentum space. It's a directed diffusion in momentum space, which describes these many singular small momentum transfer scattering processes. And after I've derived that, then it's very easy to solve this beast. And here's the result. So you get a temperature-dependent mobility, which is drawn here. And the most fun part of that is when you now look at temperatures, which is small compared to the bandwidth of the Vison, so really the low temperature limit, then you get a completely universal mobility, which is just fixed here by the Majorana velocity and temperature, and all other factors like Majorana mass, hopping rates, everything else drops out completely, and you get this completely universal result without any free parameters. And importantly, you see this mobility is diverging. So it goes like 1 over t square, which in other words says this is an asymptotically free, nicely mobile, well-defined quasi-particle. Good. So this was the case for ferromagnetic coupling, but you remember antiferromagnetic coupling, there was this interference effect. So we need to have a second thought on that. So we said in this situation, we have this perfect destructive interference. But it's not true anymore when we let Majorana scatter. So the scattering from this Majorana can obviously disturb this interference process. Therefore, there must be a Majorana-assisted topic process in the system. That you can easily calculate from some golden rule formula. And you find out that the mobility actually becomes a constant in a certain temperature range. But at low temperature, so this is in the regime where this Majorana-assisted incoherent hopping dominates. But at low temperature, there are higher order processes which are again coherent, and then we go back to our universal mobility. Good. So now we can fill out this question mark. And main message is the single Vison is indeed a highly mobile quasi-particle, and as an added benefit, you get this universal low temperature mobility. Now, what I haven't talked to you about yet was what happens when you do the perturbation with the magnetic field, which is especially interesting for this experiment also. And actually, I have to say, in our first version, we messed that up a big way. So only now we understand that correctly. So magnetic field turns out to be much more subtle than the other cases. So linear magnetic field, you get again some Vison hopping. But at the same time, now for this pure Kitaev model to cubic order, you open a gap in the Majorana spectrum. And what happens that this at each Vison gets a Majorana zero mode, and the size of the wave function of this Majorana zero mode goes like 1 over the mass of the Majoranas, or 1 over h cubed in the system. And that Majorana zero mode turns out to interact very strongly with other Visons. So, and this leads to awful behavior also of numerical quantities. So let me show this to you. So this is now the Vison hopping rate, calculated as a function of this mass of the Majorana fermions. And there's a simple scheme. That's when this Vison distance is much larger than this correlation length of the size of this zero energy bound state. There, everything is perfect. You get here a well-defined hopping rate. Everything is easy. And you can forget what's written down here. That's some matrix element to some excited states. But in the other regime, really hell breaks loose. So when you calculate hopping rates in different directions, you get different results. And you also have to take into account not only this ground state to ground state hopping process, but also excited processes. And so in this regime, we get a surprisingly strong long-range interaction. And I emphasize this because it was not present in the case of this gamma term. Yeah? So for this gamma perturbation, the mass was zero, but there was no such problem whatsoever. Here, the situation is very different. Here, everything becomes complicated and difficult. But for in this regime that these Visons are really far away from each other, we are safe. And we can do this for the ferromagnetic case. In the antiferromagnetic case, there's again an interference effect, and the rates are much smaller. But here something interesting also happens, namely the Vison band obtains a Chern number in this case. Good. And so let me finish now with a kind of thing which we thought quite a bit about and where we changed our mind quite dramatically. So if you look at the experiment, that was this quantized kappa xy, which you see in the experiment as function of temperature. So this quantized thermal Hall effect coming from this edge mode. But if you look at the experiment, there's a rise, and you see this better on this scale. There's a big hump on top of this quantized signal, which also has a very big amplitude. And so the question is, where is this coming from? Yeah? And one candidate for this is that it comes from the Visons. So could it be that this peak arises from the intrinsic Hall effect of thermally excited visons in a paper in the system. And if you look, what we first thought is that the answer is yes, but that was based on some errors in our calculation. And now we've changed our mind, and we believe this is not due to the visons, because for the ferromagnetic Kitaev model, which is the most likely candidate, there are anyhow no Chern bands for visons. And in the antiferromagnetic model instead, we would expect a dip and not a peak for most field directions. Good, so let me stop here. So I want to discuss, I want to answer one generic question, namely what are the properties of a really quantum dynamical Vison in a Kitaev liquid? And this can be answered by a controlled perturbation theory. So we really know this in a controlled calculation what happens. And we find that the Vison is a highly mobile quasi-particle, but there were some surprises like these interference effects, which we didn't expect. And another nice property is that one gets generically such a universal high temperature mobility. Another surprise was that there's a substantial long-range Vison-Vison interactions in the presence of a magnetic field. That's what we didn't. So the hopping rates are strongly influenced by the presence of a Vison at quite some distance. And there's also a story of Chern bands, but unfortunately, maybe not related to the experimental systems, but obviously our future work will concentrate on seeing more experimental signatures of dynamical visons. Thanks.